of Somalia. I'm going to open the SIWA-Somalia model in VENSIM and sort of walk through the paces. This is the same model that we looked at in the lecture. So here it is. This is the general structure of the model. I'm going to go first through the stocks and fluxes, and then the auxiliary variables. As you can see, the model, as we discussed in class, has three major stocks, or three principal stocks: population, which is located here, the freshwater sources located here, and the freshwater supply located here. This model, because of the number of variables that are involved, actually makes use of what I would call secondary stocks. And these are some other of these box variables here, like consumed water, water and sewer treatment, runoff, leakage, non-recycled water, which are also stocks. They don't happen to be part of the main governing variables of the model, but they're still useful to look at the system. Okay, so these are also defined, and then we have the rest of the fluxes. So let me start with perhaps the simplest one, population. And population we've been dealing with consistently through the class. Population is controlled by a birth flux and a death flux, in and out, respectively. Births are driven by a birth rate. Deaths are driven by a death rate, and this also has an immigration flux here that's driven by an immigration rate. And the equations for those are fairly straightforward. Population is given as births plus immigration minus deaths. Okay, and it's got an initial population value. In this case of Somalia, this initial population, it's given as 9 million people. Okay, the birth rate in this case, it's this would be essentially 0.36%. So this is people per month per people. So this is one thing I should say is that the time step here is in months. So this is the monthly rate. This is in 0.0036, which would be essentially it would be let's see, 0.36% per month. Okay, so that's not a yearly stock. Okay, and the death rate is I mean, same deal. It's about a third of the birth rate, just roughly, also in months. Okay, let's see, immigration is given here. In this case, I think we're running a base case of immigration of 0, which is probably okay. For Somalia, we could actually have a negative immigration rate indicating population loss to immigration, so we can do that as well. So that's a new tweak to the population model. Now there's an initial population that we just discussed, and that drives a couple of things, and I'm going to get to this part of the model sort of sequentially, because this contains, for the most part, definition of parameters and coefficients that are used in the water model. But let's start with this side. There's a base demand that drives the total demand, and the base demand is given as in the units of cubic kilometers per month. So the units of the water volume in this model, because it's nationwide, is in cubic kilometers, and the time scale is in months. The demand that drives the consumption rate. Okay, the consumption rate's got a couple of variables associated with it. There's a transfer efficiency, and we're going to get back to this in a second when we look at the freshwater model part of the model, that also drives a leakage rate. The population also drives the collection rate. That's the collection rate that is in the system for treating water after it's used. I think the other parameters are going to be pretty much defined on this side, so I'm going to skip them here. Let me go to the water side. let's look at the freshwater sources. Essentially, freshwater sources, they have an initial value. So this is a stock, and if you look at the equation for that stock, you have, it's essentially the balance between the positives and the negatives. There's an initial value of the sources, which we'll see in a second now. And if you look at the equations, the ins and the outs, essentially you have, in this case, you have the precipitation, which we'll see in the sketch in a minute, the river inflow, and then you have negative evaporation, negative river outflow, and then there's also some other positives that come as return flow, the leak to sources, and the non-recycle to sources, and the runoff to sources. So let me actually go to this schematic and show you these. So the freshwater sources stock, the ins are the river inflow, okay, at rainfall, precipitation, okay. Those are essentially the two major ins from the outside, okay. The two major outs are evaporation and a river outflow. I should mention that in systems where groundwater is an important contributor to water sources, this river outflow, river inflow are meant really as are really meant to be all water sources in and all water going out, and that may include surface and groundwater, okay. And that might actually be the case in Somalia, where groundwater is a pretty arid region, so groundwater is probably a big part of the water balance. Now there are also some ins into the freshwater sources that come from returns. I'm gonna mention these as I complete the cycle. But you know, the freshwater sources are tapped through collection to become freshwater supply. Freshwater supply is essentially the stock that's used to reflect the water that's actually usable, that's accessible for use. Okay, the sources is water that's there, but unless there's the infrastructure to collect it and to make it available, and this has to do with tanks and pipes and distribution systems and all the water infrastructure, it doesn't really become usable. So the freshwater supply stock is fed by the freshwater sources through collection, okay, and it's got an initial value, and let's continue going through the cycle. Once the water is in supply, there's a few things that happen to it. A big part of it is consumed. That's why we make it available, and once it's consumed, it becomes part of the consumed water stock, okay. The consumed water, there's a couple things that can happen to it. Well, one, it gets consumed, and when it gets consumed, it goes back into the system for treatment, okay, or it gets consumed and it really doesn't get collected, and this is the kind of water you consume and you sort of dump into the system back as runoff, okay. It becomes part of the runoff stock, and the runoff stock, part of it just goes away to the ocean or to a discharged surface water body, and this is the case in Somalia. It goes to the ocean. A fraction of it goes back into the sources. It returns back, and this might be, for example, infiltration into groundwater, or goes back to a river that is used to, again, as water source. The other part of the consumed water that it doesn't go into runoff, goes into sewer treatment. Part of the water that's treated, it's recycled and it goes back to supply. Part of sewer treatment that's not recycled goes into the non-recycled water. Okay, non-recycled water's got two things to do. It gets dumped into a surface water body to the ocean, or it goes back to the sources. Okay, part of the other fraction of the freshwater supply that's not consumed, and all freshwater supply systems have got infrastructure issues that may cause leaks. So part of that, the other fraction that's not consumed, it's essentially what's referred to as unaccounted for water. This water that leaks into the system, it becomes part of the leak stock. The leak stock's got two things to do. One, it continues to leak and goes all the way to the ocean, or it actually leaks back into the sources. You know, it gets water drips from a pipe. It goes into the ground. It becomes groundwater. It becomes part of the source again. Okay, so that is sort of the the cycle, and in the exchange between these two. Each of the pieces of the cycle, each of the steps, is driven by coefficients, and one of the things that we did in this model was to use these ratios, and these ratios are essentially proportions of water that get used one way or the other. For example, we have if you take the case of runoff, runoff, once it gets generated, once water goes into the sort of the open environment, it's got two things to do. It continues flowing out of the system, it goes to the ocean, or it goes back to the sources. Now, to do that split, we use this essentially, and I go back to the equation mode, this runoff to sources ratio, which is a fraction. It's a coefficient. It's between 0 and 1, and it tells you what proportion is that water partitioned, and in this case, this is 20% in this simulation, and this shows what fraction of runoff water returns to the sources. So this essentially 20% of this runoff. Let me go back to the schematic here. 20% of this runoff goes to the sources, and the other 80% goes to the ocean. And we do this in several of the situations. We have a consumption to sewer ratio of 0, which means that for the most part in this simulation, the water that's consumed, goes 0 of it gets to the sewer. Okay, that means pretty much that water, in this case of Somalia, there's consumed. Once water is used, it's completely thrown away. There's no treatment for consumed water, and that means, of course, there's no recycling, and certainly so essentially this link in this simulation is there's 0 flow. Okay, let's look at the leakage, and if we look at the leakage to sources ratio is 30%. So this means that of the proportion of water that leaks, so this is the supply, other portion that leaks, 30% goes back to the sources, 70% goes to the ocean. Okay, and so on. And we've defined a number of those ratios that you can explore. So, case of Somalia, let's take let's just run this model as is, just to see what the results are. And if you do that, if you just click on the simulate button, then you see the bottom graph here. And I showed some more graphs of this in the lecture itself, but in this case, you can see that with the set of parameters that it's in the simulation, over the period of 100 months, so this is roughly 8 years or so, the blue is the sources, and the red is the supply. And what we're finding out here is that at some point in the near future, the supply catches up. Essentially, the sources are run down, and they catch up with supply. So this means that at some point very soon, your need for supply, it's going to overwhelm the sources that are available, and you essentially run into the situation of a water deficit, where you really have no water to draw. So that basically means that this guy, it grows faster than this one. Okay, and actually in this case you can see that the essentially this catching up over 10 years. One of the things you can change, and in the model, you can start playing with the parameters. And if you were to run this in synthetic form, just to see what you can vary, let me say no here, and let me just change this to a variable input simulation. Okay, then you can look at all the parameters that you can tweak, and it's fairly substantial. So one of the nice things of doing a model like this is that you can actually explore sensitivity to any of these parameters. Initial population, immigration rate, birth rate, and all these, and you can actually see what's going to be the impact on the supply. One of the parameters that this model was very sensitive to is the efficiency in the transfer. If you tweak this, you can see very quickly that this parameter changes this ratio here significantly. I'm going to stop this, and I'm going to focus on this parameter. Let's see. Let's have it. If you go to this transfer efficiency, and this is essentially the ability of not losing water. Okay, so this is and what this is saying here is that of the water, there's a 70% of water that it's transmitted from sources to supply. So when you have the water in the supply, there is there's essentially an efficiency that splits between consumption and leakage. Okay, so if you're here, you have consumption and leakage. That means that there's a 70%. For if you have 100 drops of water that are used, 70 get actually consumed. The other 30 are leaked. And by tweaking that parameter, just up or down a little bit, this is essentially reducing losses. If you're able to improve on this number, it can have dramatic effects. And if actually this number gets worse, then the system is very variable. So I'm gonna rerun the simulation. Let me rerun it again with those values. Actually, I want to go back to the. Let me say no here, because I want to go back to the base case. So I'm actually. Let me see. Let me cancel out of this. And so right now, it's pretty sure. Let me just. I'm just going to overwrite it. And okay, so we go back to 70%. This is what you get. Okay, if you tweak that number, let me tweak that number up to, let's say, 90%. So let's say you improve efficiency by a couple of points from 70% to 90%. I'm going to run that again, and I'm going to overwrite just so we simplify this. You can see now that essentially the time at which this crossover between the sources, which are in blue, okay, and the supply, you actually reach a point where you're able to curb the supply, and then your sources are able to exceed your supply. So you're making more efficient use of your sources. Okay, you can actually do the other, another example, and for the transfer efficiency. And so this is a variable upon which this model, it's if you had a 50%, and actually 50% is more typical of many countries around the world. Just to give you an idea, in the US, our transfer efficiency overall, it's probably in the 70% ratio, so we're not doing that great either. But a lot of countries have like 50%, so that means that half of the water is leaked. If you do that and rerun it, and we'll overwrite this again, you can see now it's the situation has gotten a lot worse, where your sources are not able to catch up. And it happens very, very quickly within a few years. So let's see. Well, you can play further with this model. It's the same model structure that we have with with the U.S. case as a whole and with the case of Arizona. So I encourage you to play around with this model quite a bit, and see what you learn. And again, post your insights on our Facebook page, and I look forward to some more discussion. Okay, so I hope you enjoy this video.